All right, I'm going to give this a go. I am using a different whiteboard program this time. Let's see how it works. So we have some paper 1 questions on simple harmonic motion. There are 18 of them, hence 18 marks. So first guy is simple pendulum, simple harmonic motion. It tells about gravitational potential energy at the equilibrium position. It says that it's 0. That makes sense because it's the lowest point. How many times during one oscillation is the kinetic energy equal to the gravitational potential energy? Be careful with this one because I was reading that as where is the kinetic energy equal to 0? But that's not what it's saying. It said when is kinetic energy equal to gravitational potential energy? And it's actually 4 times in the cycle. So here we have a pendulum, and we have the highest point and then the lowest point. And when a pendulum is at its highest point, when we're at the highest point, that's where the displacement is equal to the amplitude. That's maximum potential energy and no kinetic energy because it doesn't move at the highest point for that split second of time. And remember, of course, just because it's not moving at the highest point doesn't mean it's not accelerating. In fact, that's where it has its highest acceleration, because in a simple harmonic oscillator, the acceleration is proportional to the displacement. And we remember, of course, that just because something isn't moving doesn't mean it's not accelerating. Think about when you throw something up into the air, up at the highest point, the velocity for a split second of time, as time goes to 0, you could say, is the velocity there is 0, but it is still accelerating due to gravity. And then at the lowest point of the pendulum, where x equals 0, that's the equilibrium condition, the gravitational potential energy is 0 because it's at its lowest point, and the kinetic energy is at a maximum. But that doesn't describe where kinetic energy equals gravitational potential energy. And that is at those 2 points right there. Those are kind of like the in-between points between the amplitude point and the equilibrium point down on the bottom. Now it says during one oscillation, when is this true? So in other words, in one oscillation, one of those points hit. So if we start from over here, and then we swing through to this side, and then we swing back to the other side, then we actually hit those points that I highlighted 4 times in the complete cycle. So the answer is D, 4 times. Okay, next question. Correct for tangential acceleration of a simple pendulum. So a simple pendulum is a simple harmonic oscillator, and we know the conditions for SHM. The acceleration has to be proportional to the displacement, and the acceleration points towards the equilibrium point. In other words, it opposes displacement. Since this is a definition, we have to be careful that it looks like, let's see, proportional to the displacement. It looks like choice B would be the answer. But notice that D says proportional and opposite to displacement. And you have D would be the better answer. D is the correct answer. As I was just discussing with Ms. Coleman, this is a definition question. So on definition questions, they may include incomplete definitions as wrong answers. So you have to pick the best choice. Number 3, a mass spring system. This question hinges on that fact. It's a mass spring system. Oscillates with a period t at the surface of the Earth. You go to Mars, it's 0.3 g. What's the period on Mars? So we refer to the data booklet, and we see that mass spring has a period of 2 pi radical m over k. Notice that g is not included in that expression. In fact, g is included for simple pendulum, so a simple pendulum would be affected, but a mass spring pendulum is not affected. It winds up having the same period on Earth as on Mars, choice C. Okay, let's continue to number 4. I was hoping to avoid that bell. Oh, well. So, number 4, we have a simple pendulum and a mass spring system, and they're oscillating with the same period. Said the mass of the bob and the mass of the spring are initially identical, but then they are both halved. And what is the ratio of the periods now that the masses have been changed? Let's look at the formulas for the periods of simple pendulum and mass spring. We can see from the equations for period for pendulum and mass spring that pendulum does not depend upon the mass of the pendulum bob, but the mass spring setup does depend upon the mass attached to the spring. This is 2 pi radical m over k. So if we were to half the mass, it would have no effect on the pendulum period, but it would have a radical 1/2 multiple effect on the period of mass spring. So if we do pendulum divided by mass spring, that's 1, because the pendulum period would not change. So that's 1 over radical 1/2. And so if we simplify that, we wind up with radical 2 is the period of the pendulum over the period of the mass spring system, if you have both masses. So 4 is choice C. Number 5 is like kind of a trick question. So I'm reading number 5 and I'm like, okay, so displacement, when displacement is amplitude divided by 3, the speed is v. What's the speed when the displacement is equal to the amplitude? Thinking in my head it's the equilibrium point, but that's what I read one thing, my head thought another. So I'm looking in the data booklet and I see that there's a formula for speed, which is plus or minus the angular speed times the square root of the amplitude squared minus the displacement squared. And I'm like, oh, maybe I can do something with this. But then I reread the question and I realized when the displacement is equal to the amplitude in any SHM system, when the system is at maximum displacement, when you're at the amplitude position, the maximum displacement, the speed is 0. Even when you look at the expression v equals angular speed plus or minus the square root of amplitude squared minus x squared, if amplitude and x are the same, then your speed has to be 0. So yeah, 5 is A. All right, next question. This one's got me a little bit stumped. Mark scheme says D. Now I'm going to give my best estimate as to why. These can be approximated as simple pendula, even though they're kind of not, because a simple pendulum assumes kind of like a point mass for the bob at the end of the string. These are not point masses. But we can consider the mass distribution of the bob for each of these pendulums. And this is a ballpark estimate, but the center of mass for A and B is kind of like in their center. They're evenly constructed, and so in the center of the shape. Whereas the center of mass for C, it seems to be wider towards the end, so the center of mass would be a little bit closer towards that wider end, whereas for D, the wider end is closer to the pivot point, and so its center of mass is actually going to be a little bit higher. And we know that the period for a simple pendulum is 2 pi radical L over G, and so the longer the length of the pendulum, the longer the period of that pendulum. And so D, having the least length, the shortest length, would also have the shortest period, giving us choice D. That would make the most sense. I can't imagine anything else. I mean, you can do rigid body mechanics, but that is way beyond the scope of this class. So I'm pretty confident that one, I know it's the answer because I looked at the answer key, but I'm also pretty confident in the explanation as to why. That's it for this page. Let's go to the next page. Although for number 5, they didn't give us a little recording box. I don't know. I suppose it doesn't matter. If they give you a little box, you have to write the stuff, make sure you write the stuff in the box. All right, this page only has one problem on it. We have number 7. Okay, so first and foremost, we have a couple of different formulas for velocity. And I can see that from all of our answer choices that it has to include t. So velocity is a function of time, not velocity is a function of position. We have 2 formulas for velocity as a function of time. V equals omega x naught cos omega t, or V equals negative omega x naught sine omega t. And so we have to pick one. Well, the one we choose we know comes from the starting conditions. And I can see from the graph that when time equals 0, the starting position is at the amplitude point, not at the equilibrium point. So at time equals 0, x is not 0, x is x naught. And we know that from SHM that when you are at the equilibrium point, your speed is 0. I think I just said when you're at the equilibrium point. When you're at the amplitude point, when x equals x naught, when you're at the maximum amplitude, your speed is 0. My bad. I wrote down the right thing, I just didn't say the right thing. So then, in order to make that true, then when time equals 0, then v equals 0, we have to use the sine expression because we know that sine of 0 is 0. If we use the cosine expression, cosine of 0 is 1, that would not get us where we need to be. Okay, so we're getting there. But if you look at the answer choices, none of them include omega. That's because they have omega is 2 pi over the period, which is also in the data booklet. So we can substitute that in. We can also see, which I think is another dirty trick when I was just banging my head against the desk for about 5 minutes, that the period, the time for one cycle here, let me get my highlighter, the time for one cycle, which would be the period, is 2t. So capital T is equal to 2t. Not really sure why they decided to do that, but no one asked me. And the initial amplitude condition is that x naught is negative 2a. So let's do some substituting. All right, let's clean it up. The 2's cancel, the negatives cancel. Not all of the 2's cancel, there's one left over. And so we wind up that the speed, or I should say the velocity, because negatives matter here. I suppose the direction does matter. V equals 2 pi times the amplitude over the period times the sine of pi t over capital T. I shouldn't say the period because the period is actually 2t. The IB loves to reuse terms over and over and drives me a little bit crazy. But in any case, the answer is choice B, which agrees with the mark scheme. All right, let's proceed. I'm also going back. I think you actually have to write your answer choice in the recording box. I forgot to do that before. That was an app. Can we compare this, where the force is 0, to this beast of a question, number 7? I mean, really? I don't know. I'm still kind of my bell is still rung after that question. On this page, we have 2 questions. We have graphs of acceleration versus displacement. That shouldn't be too complicated. Yes, this one is much more reasonable. I thought the last one was a little bit much. So we have, one, you should know the conditions of acceleration versus displacement for SHM. It's one of the biggest deals in the entire topic, but they also give us a formula for it. A equals negative omega squared x. So I know that acceleration versus displacement is going to be linear, and so that automatically eliminates choices A and B. I also know that the acceleration is negative, whatever the displacement is, so if I have a positive displacement, the acceleration is negative. If I have a negative displacement, the acceleration is positive. What does that leave us with? Choice D. All right, number 9. So we says something going under SHM has a period T, total energy E, amplitude is halved. What happens to the period and the energy? Well, the period of a simple harmonic oscillator is not related to its amplitude at all. You can see in any of the equations that refer to the period, amplitude is not included in those expressions. In fact, if we look at pendulum or mass spring, in neither of those equations does the amplitude have any, in neither of those expressions does amplitude have any effect on the period. So I know that changing the amplitude doesn't affect the period, so it's not A and it's not B. But what does it do to the energy? So total energy, the formula for total energy is given on the data booklet, where it's 1/2 m omega squared amplitude squared. And we said that omega naturally, omega is 2 pi over the period. But as we said before, changing the amplitude does not affect the period, so the period is going to remain unchanged. But the amplitude does affect the total energy. We can see that, there it is. Total energy and amplitude are related. In fact, total energy is related to the square of amplitude. So if you were to half the amplitude, then it would quarter the energy. And that, of course, is because the amplitude is squared. So if you half the amplitude, square that, that is 1/4. And so I'm left with the same period, but 1/4 the energy, choice C. Okay, terrific. Next question. Where was that problem? Page 5 of 7. All right, we're making progress. Let's go. Of course, this program has decided how many problems appear on each page, so it's rather kind of arbitrary. All right, enough yammering. Let's go. All right, reading number 10, blah, blah, blah. You take a simple pendulum and a mass spring pendulum, and you take it to the moon. The moon, of course, has less gravitational acceleration than the Earth does. And it says, what happens to the period? Well, let's look at the periods for pendulum and mass spring. Okay, we can see that mass spring, the acceleration due to gravity has no effect on mass spring, so taking it to the moon will not affect its period. So mass spring will have the same period, so it's either A or B. But if we go to the moon has a smaller acceleration due to gravity than the Earth does. Oh, okay, stop that. All right, this seems to be annoying. Actually, I'm going to change the color, blue. So there's a smaller acceleration due to gravity than what the Earth has, and even though, yes, there's a square root there, the g is in the denominator, so a smaller acceleration due to gravity would mean a greater period, which makes sense because, of course, the pendulum would fall more slowly on the moon. So if we took it to the moon, the simple pendulum would have a period greater than the starting period, but the mass spring would have the same period, giving us choice B. Alrighty then, next question. We have a simple pendulum. At which position is the resultant force 0? So this one is a little bit tricky, and you might be tempted to say that, well, first of all, the net force is 0 where the acceleration is 0. And then you're like, okay, well, where is the acceleration 0? So if we're talking about a simple harmonic oscillator, the tangential acceleration, now I'm not talking about the centripetal acceleration, but the tangential acceleration of the system is given by negative omega squared x. Okay, so then you might be like, all right, well, if x is 0, then the acceleration is 0. And where is x 0? But in the equilibrium position, down at point B. So you might be tempted to say point B. In fact, the pendulum bob is still accelerating at point B. It just doesn't have any tangential acceleration. So that would be true. However, don't forget from circular motion, there is an inward pointing acceleration that's given as the speed squared over the radius. Now granted, a simple harmonic oscillator, the speed is not constant, so that centripetal acceleration does change over the course of the oscillation. But at point B, there is a centripetal acceleration. In fact, the centripetal acceleration is a maximum at B because that's where the pendulum bob is the fastest. So at every single point in this oscillation, there is an acceleration, whether there be a tangential acceleration or a centripetal acceleration or combination of the two. And so therefore, if there is an acceleration, if we have ourselves an acceleration, then we have ourselves a net force. So at which position is the resultant force 0? Nowhere. Choice D. And I say it's tricky because we have simple harmonic motion on the mind. I mean, I actually first answered this question as B. I was thinking SHM, and I was like, oh, there's no acceleration where the x is 0. Okay, next question. Hold on. Don't forget that there is still a centripetal motion component. There's also the weight of the pendulum bob pointing downward, but that weight is also countered by components of the tension, but still, down at the bottom, while the pendulum is in motion, right, it says oscillates as shown. While the pendulum is in motion, there's a centripetal acceleration. When the pendulum's not in motion, there is no centripetal acceleration. There is no acceleration at all. It's not in motion. But while it's in motion, there's a centripetal acceleration, and therefore there is a resultant force. So yeah, choice D. Okay, number 12. So we have a spring, and it says we have a simple harmonic motion, simple harmonic oscillator, and it says the amplitude is A and the total energy is E. It says what happens to the total energy when you increase the mass by triple and you increase the amplitude by double. Let's take a look at the formula for total energy. Okay, terrific. So it says the mass is tripled and the amplitude is doubled. And you might be tempted to say that, oh yeah, the angular speed is a constant, sure, and the mass is tripled, and the amplitude is doubled, and that's squared. So you just say 3 times 4 is 12. The answer is C, and you would be wrong. Let's dive into that angular speed. So angular speed is inversely proportional to the period, and we're talking about a spring mass system, and so the spring mass system period. So what this means that if I were to triple the mass, that would radical 3 the period. All right, and if it radical 3's the period, I can bring that back into the angular frequency. Again, we have that right there. So if I triple the mass, I radical 3 the period, and that's 1 over radical 3 for the angular speed. Again, we're talking about proportional changes here. So yes, if you triple the mass, that angular speed is not constant. In fact, the angular speed changes by 1 over radical 3. If we were to square that, we would get 1/3. And of course, 1/3 times 3 is 1. So that cancels at that portion. And so we have 2 squared, and so that total energy would actually be changed by a factor of 4. The answer is B, not C. Very interesting. All right, let's do number 13, and let's go. So 13, we have a pendulum, an oscillating pendulum, simple harmonic pendulum that goes to Mercury. So again, the period of a pendulum, a simple pendulum, is 2 pi radical L over G. And it says that that pendulum went to Mercury where the gravitational field strength is 0.4 what it is on Earth. And so we have that the period is proportional to radical L over G, and if we kept the same length in terms of a proportional change, we would get length is the same, G is 0.4 what it is on Earth, and that of course gives us a proportional change of 1.6, and that would be choice C. Okay, let's move on to page 3. I think, what did it say? There were 18 problems in here, so we're getting near the end. And we'll continue with number 14. Okay, 14 tells us the total energy of the system is 16 joules, and what's the kinetic energy when the displacement is x naught over 2. So we do have an equation for kinetic energy, and that's on the data booklet. So there's our kinetic energy formula. Now, the mass is the same. It's not changing the mass, so it's the same mass. And omega is the same because omega is 2 pi over the period, and changing the displacement of the system doesn't change the period. So the 1/2 m omega squared, that's going to be the same if I change the displacement. And so really, I'm looking at a proportional change here. We're changing displacement from amplitude to 1/2 the amplitude. So that kinetic energy is proportional to amplitude squared minus displacement squared. Now, I said earlier that the angular speed was not constant. At first I was like, oh, it's constant. Oh, hey, but guess what? It's not. But remember that angular speed is 2 pi over the period. So you have to think about if the changes you're making to the system would affect the period. This says it's a mass oscillating. It doesn't actually say what type of system it is, but let's just say that it's mass spring. So if you were changing the mass of the mass spring system, that would affect the period and thus would affect the angular speed. Or if you had a simple pendulum and you changed the length, that would affect the period and that would affect the angular speed. But changing the displacement of the system doesn't change the period of the system, no matter if you're talking about a pendulum or mass spring. That's probably why they didn't say what type of pendulum it is. So my point is that by changing the displacement of the system, it does not affect the period, it does not affect the angular frequency. I'm not changing the mass either, so that's why I can say the whole first part of the expression is constant. I can drop it out when talking about a proportional change. No problem. And so, yes. Now, my displacement is half the amplitude. So what I can do here, if I'm going to say that the amplitude is 1 and my displacement is 1/2 the amplitude, in terms of a proportional change, I can say the 1 I'm using for amplitude here means that the amplitude has not changed. That's the same. That's a constant. But my displacement is half of that amplitude. That's why I put the 1/2 there. So 1 squared minus 1/2 squared would be 3/4. And then it's like that is the actual proportional change. So if the original energy of the system was 16 joules, 3/4 of 16 joules is 12 joules. Choice C. Looks like 15 is a similar question to 14. It says we have simple harmonic motion, has amplitude x naught. It says maximum kinetic energy is EK. Well, the maximum kinetic energy, assuming that this is a system that it's not losing energy, maximum kinetic energy will be maximum potential energy, will be the total energy of the system. So when it says that the system's maximum kinetic energy is EK, that is really saying that the total energy of the system is EK. So it wants to know what's the potential energy of the system when the particle is 0.2 times the amplitude from maximum displacement. So we don't have a formula for that. However, so at any given point, the total energy of the system, of course, is the sum of the potential plus the kinetic. So if we know the total energy of the system, and we don't have an equation for the potential energy, we kind of do. We can use the equation for kinetic energy. And the reason why we care about that is because we do have an equation for kinetic energy. Okay, so I started to write out the solution, then I reread the question, especially when I worked it all out and I wound up not getting an answer that was listed. Yay! But then I reread the question and I realized that it's a little bit awkwardly phrased, but my approach is correct, my formula is correct, my setup is correct, but the point 2 is not correct. So let me address that. The amplitude, again, the way I'm setting this up is right. We have x naught, representing that as 1, and then x, I was like, oh, x is 0.2 times x naught, so I put in a 0.2. But hold on a second. The x, the displacement, we don't measure displacement from the amplitude position. We measure displacement from the equilibrium position. And the question says, what is the potential energy of the system when the particle is 0.2 x naught from maximum displacement? We don't measure from maximum displacement. Displacement, x, is measured from the equilibrium position. So if I'm 0.2 away from the maximum displacement, what I'm going to put in for x is not 0.2, but 0.8. So just as a reminder, in terms of the way pendulums or simple harmonic oscillators work, the equilibrium position, in this case I'm assuming, it doesn't matter if it's a spring or if it's a simple pendulum, I'm going to say simple pendulum, the rest position, the lowest position for a simple pendulum, that's the equilibrium position, and we say x is 0 there. We don't say x is 0 up at the highest point, the maximum displacement, that is the amplitude position. We see that x is equal to x naught. So it is when the particle is 0.2 x naught from its maximum displacement. So if we said that it says when a particle is a distance of 0.2 x naught from its maximum displacement, that's where it is. It's not 0.2 x naught away from the equilibrium position, and that's where we measure displacement from. So if we're 0.2 away from maximum displacement, the actual displacement, if you were to describe it, would be 0.8, not 0.2. And so if I put 0.8 in for x, 0.8 squared is 0.64, and 1 minus 0.64 is 0.36. Okay, and then you might be like, oh, look at that, 0.36 is an answer choice. It is not choice B. We have to go back to the original point where they're asking about the potential energy, not the kinetic energy. We get that the potential energy is the total energy of the system, EK, minus 0.36 EK. I wrote EX, that's EK, that's better. Therefore, the potential energy is 0.64 EK, and the answer is C. Yeah, so talk about close reading a question. At least if you put in 0.2 in for x, you would get 1 squared minus 0.2 squared gets you 0.96. And 0.96, neither 0.96 nor 0.04 are answer choices, so at least they tip you off that you were not on the right path, and maybe you should reread the question. All right, 16. So here's an interesting question. We have a mass spring system, and it's doing simple harmonic motion, and it says, which is independent of the initial displacement of the spring? Okay, 16 is not as bad as 15. So basically what I went through, I went through all the answer choices and I wrote down the equations. I didn't write down the equations for speed. You can look them up. They're a little long for this space. I can read them off. We have the speed is either omega x naught cos omega t, or negative omega x naught sine omega t, or plus or minus omega square root x naught squared minus x squared. But the point is that all of the expressions for velocity include amplitude. And so that initial displacement of the spring would be the amplitude. So it is not average speed. It's not total energy, because that includes amplitude. It's not maximum kinetic energy, because that's the same as the total energy. It is angular frequency, and we can see that angular frequency is 2 pi over the period, and period's 2 pi radical m over k, having nothing to do with displacement at all. So that would be A. Cool, let's go to 17. 17 doesn't look too bad. It's talking about a simple pendulum and its period. So let's write down the formula for the period of a simple pendulum. I can see that mass does not affect the period of a simple pendulum. It would affect the period of a spring pendulum, the mass spring system, but mass has no effect. So 4m mass, I don't care what you're doing to the mass, it has no effect. But L is in the expression, so 1/4 of the length is going to affect the period. So proportionally speaking, g of course is a constant, that stays the same, but we have 1/4 the length, so square root of a quarter, square root of 1/4. Square root of a quarter, of course, is 1/2. So if I have 1/4 the length, it will be 1/2 the period. That is choice A. And so 17 is choice A. All right, and then on the last page, this guy right here, it says, which of the following experiments provides evidence for the existence of matter waves? I don't know. The answer is electron diffraction, because electron is a matter particle, and so the fact that electrons diffract around crystals means that they have a wave function, the de Broglie wave function. What does this have to do with SHM? I have no idea. I do not think this is an SHM question. I don't know why it included it. So there you go. But that's it for these 18 problems. That's what Question Bank gave me for the 9.1 questions. So congratulations, we're done.